f of x is equal to x squared plus x divided by x minus 1. So to start off, we'll find vertical asymptotes, if any. So we look at the denominator. So if we set that equal to 0, you just have to add 1 to both sides. So there is a vertical asymptote. There's just 1 at x is equal to 1. So for horizontal asymptotes, we're going to look at the degrees of the numerator and the denominator. So the degree of the numerator is equal to 2, and the degree of the denominator is equal to 1. So for horizontal asymptotes, that means there's none. For oblique asymptote, though, that means there actually is an oblique asymptote. So if the degree of the top is 2, the degree of the bottom is 1, the degree of the numerator is exactly 1 more than the degree of the denominator. That means there is an oblique asymptote. So to find it, we're actually going to go ahead and use polynomial division. So again, we can use synthetic division here. So I'm going to go ahead and use synthetic division. So start my synthetic division here. So since x minus 1 is in the denominator, a 1 goes out front. The first coefficient is a 1. The second coefficient is a 1. And since it's missing a constant term, the last number there is going to be a 0. So I bring down the 1. 1 times 1 is 1. So I add vertically. 1 plus 1 is 2. I multiply 2 times 1. And then add vertically. 0 plus 2 is 2. So remember, with oblique asymptotes, the remainder doesn't matter, but the numbers before the remainder do. So we have an oblique asymptote at y is equal to, so the first value there, the 1 is the x, and the 2 is the constant. So our oblique asymptote is going to be at y is equal to, I'm just going to write it as x plus 2. So let's go ahead and graph our asymptotes before we go any further. So here we've got our vertical asymptote at 1. So let me just draw my vertical line here. So x is equal to 1. So to graph our oblique asymptote, it's not going to be a horizontal line. It's just going to be a linear equation, though. So y is equal to x plus 2. Well, I could say that the y-intercept is going to occur at 2. So I'm going to put a point right here. And then the slope is 1. So that means 1 over 1. So I can move up 1 and right 1. And then that would give me a point right here. Right here. Right here. Right here. And then I can go in the other direction as well. Down 1 to the left 1, down 1 to the left 1. So this, connecting it, would be the graph of y is equal to x plus 2, which is exactly what I want to do, but I'm just going to connect it with a dashed line. So that's our line. Y is equal to x plus 2. Another boundary point, sort of telling us what's happening on either side. So let's plot some points. So we have x, we have y. I'm going to go ahead and just try to plug in x values on either side of the vertical asymptote. There's only one vertical asymptote, so I need something to the left of 1 and something to the right of 1. So maybe we can try 0 and 2. So if I plug in x is equal to 0, we get y is equal to 0. So we have the ordered pair 0, 0. And if I plug in x is equal to 2 into my original function, we get y is equal to 6. So let me plot these 2 points. So we have a point at 0, 0, and we have a point at 2, 6, which is right up here. So to fill in my graph, I'm going to use the same ideas from before. So if I start at that point that I'm looking at 0, 0 on the left side, the end behavior is to go towards the oblique asymptote, which means that it just decreases and keeps going down, but basically in the same manner that x plus 1 would move as you go out to the left. And then to the right of that point, it's just going to shoot down towards the vertical asymptote. So it connects right there. And then the same thing for the other point. So on the left, it's just going to go up towards the vertical asymptote. On the right is the end behavior portion. So it's just going to go towards the oblique asymptote.